Hi, so this is chapter 2, Precipitation. So for this course, the contents for chapter 2 is some description of precipitation, measurement, how do you measure it, IDF curve, you will know later what is IDF, rainfall data analysis, filling in missing data, and mean aerial rainfall. So how actually precipitation is formed? Say it's due to some condensation of the nuclei. Nuclei is like I don't know, like a cell maybe, in the air. Okay, so where the moisture may stick to it and then will create or develop these droplets. And then the cooling of the atmosphere, growth of water droplets, like I said before, and mechanism to cause a sufficient density of the droplets. So if the environment and the air condition, many parameters are suitable, then droplets will be created and precipitation will occur. So there are four major types of storms. Convective storms, where humid air rises. Orographic storms. Elevation relief means that usually orographic storms occur when it's near to some mountain ranges. Then the air will be lifted. Elevation, we call it as elevation relief. And number 3, like a cyclonic storms. So this is more a bigger scale of storm, where it is due to the rising and lifting of air, and it may be developed from the ocean, for example. So a cyclonic storm is a bigger storm system. Okay, and then tropical cyclones. So this is also quite similar to cyclonic storms, but it is more bigger in scale and it's more intense. Okay, so tropical cyclones. Tropical cyclones might also be, we can say it as what do you call it, a typhoon. Okay, so some might call it tropical cyclones, some might call it typhoon. Okay, so this is an example of a convective storm. Okay, it's developed quite locally. Okay, if you see clouds which is a cumulonimbus, a high cloud or a dark cloud, so it is due to the dark is due to the depth of the cloud. So from this, the precipitation can occur. Okay, so it's more local. Okay, so this is an orographic storm. Okay, remember, due to the elevation relief, so it is related to mountains where the moist air are restricted due to some mountain ranges. So, and then some elevation of the air, moisture, air and moisture. So it will condense up in the sky, and then so the rainfall may occur. So this is orographic storm. Okay, so cyclonic storm. So usually cyclonic storm is a much larger storm system. Okay, like compared to convection and orographic, it's a more small scale system. But cyclonic storm is usually related to the pressure of the ocean. Okay, different pressure of the ocean, and climatic system is a larger scale, so that's why cyclone or cyclonic storm may occur. So usually it occurs from the sea, and then it carries by wind to the land. Another example of cyclone, which is tropical cyclone. So tropical cyclone is actually it's typhoon. It's the same thing as typhoon, like I said before. So this is example of a tropical cyclone or typhoon near the Philippines and Japan. So this area, the Pacific Ocean, usually generates this tropical cyclone. Tropical cyclone, I think the word is used by the US. The United States, they use the word tropical cyclone, but us in Asia, we use a typhoon, the word typhoon. So it's the same thing. Okay, so we already see a type of storm. So storm may be small scale and maybe a larger scale. Okay, so next is classification of precipitation. Okay, so what is precipitation? So I think you should know already. It's rainfall actually, but it's not just rain. It can be snow or hailstone or sleet and also rain. So but us in Malaysia, we only experience rain, right? And sometimes maybe I don't know if there is some hailstones. I'm not sure, but maybe sometimes, but really rare. But for us, as a civil engineer, also we always deal with just rainfall. Okay, so precipitation may be snow, maybe rain. Okay, so that is all considered as precipitation. Okay, so we know we have rain, so we need to measure it. Okay, we want data. We want to quantify how much rain there is so that we can design later. So there are several types of rainfall gauge. I just put here rain gauge. It can be non-recording and recording gauge. There is a different type of mechanism like tipping bucket, weighing, float. Okay, and the data acquisition might be digital or sensor or even network. So we will see more later. Okay, so this rain gauge, it may be automatic or manual, so similar to like recording or non-recording. Automatic means that you can put the rain gauge at one place and then you just leave it. Later you can extract the data. Okay, but non-recording is maybe every day you need to collect the data from the rain gauge. Okay, we see next what is the mechanism of rain gauge. Okay, so these are usual type of mechanism. For example, tipping bucket, float type, weighing type. So the recently now most of the rain gauge are using this tipping bucket mechanism. Okay, tipping bucket mechanism. There's also like a float type mechanism. This is maybe much older mechanism used, and also weighing type. So what's the difference? Weighing type is it weights the precipitation. Okay, it's for rain and also snow. Okay, because snow might take some time to melt. Okay, so weighing type is particularly for precipitation which have a solids like snow. But for in Malaysia, we usually use tipping bucket and flow type. This is an example of a rain gauge. Where is it? Can you guess? Okay, it's here. This small uh, thing here. So rain gauge is not big. It's a small equipment, but it needs to be located at the right place. For example, there are some how to say manual or procedures where you should put the rain gauge. For example, it should be in a distance far from other high objects. Okay, and it should be put it doesn't have to be at a high place, but it should be like the radius from the center or the location of the rain gauge should be clear from other tall objects, just to make sure that the wind does not affect the amount of rainfall being collected. Okay, so this is an example from the Department of Irrigation and Drainage. Okay, so we know the mechanism. Part of the mechanism is also how the data is being is being uh, noted or recorded. For example, this to right is quite old way. Okay, for recording, where you need to have some kind of a graph paper. Okay, and then from the whether it's tipping bucket or float type, there will be like a pen which will record in the graph paper on the level of depth of the rainfall being collected. Okay, so on this left side, it is more I don't know, automatic, maybe half automatic, because we can leave the rain gauge also, but we don't need this type of graph paper. Okay, we can just download it later. Okay, so this one is I think maybe semi-auto and semi-manual, because somebody still needs to go there and collect or download the data from the rain gauge. Okay, and the most high-end ways is this kind of rain gauge automatic network system, where this rain gauge is connected to a network system and maybe automatically collected and stored in a server. So for the Department of Irrigation and Drainage Malaysia, so we have this kind of network system since, if I'm not mistaken, since 1970, if I'm not mistaken. So it's a network of rain gauge across the whole Malaysia, and the data are automatically collected and downloaded in the server. But some station is a manual rain gauge station, where somebody needs to collect and take the data every day. Okay, so this type of data acquisition method, there are several types of method. For more information on the rainfall station and instrumentation, so you can look into the Malaysia standard for rainfall station instrumentation, and also you can look into the World Meteorological Organization. So we have this kind of manuals. Okay, so next, how do we quantify our rainfall data? Okay, we want to measure our rainfall data. So we usually measure it in terms of intensity. Okay, it may be centimeter per hour, millimeter per hour. Okay, and it also may be centimeter per day or millimeter per day. Okay, so it depends on our purpose. And we may also measure it in terms of depth or total depth. Okay, for like 2 hours, how much rainfall depth there is. Okay, in 5 hours, how much rainfall depth. Okay, and then the other important is the duration of this storm. Okay, duration of storm may be in hour or days, but usually it's hour or also minute. Okay, duration of storm means there is no storm, there is some storm or rainfall, and then there is no more rainfall, so that is one storm. So the storm may be occur in like 2 hours or just 30 minutes, for example. So that is duration of storm. And the other important one is the frequency or average recurrence interval. So this is very important for civil engineers, because we need to design rainfall so that we can estimate the size and capacity of drainage, or a river capacity, or a reservoir. Okay, so this ARI frequency is very important. It's important to understand it. Okay, and then there is temporal distribution. So temporal distribution is actually quite similar to duration of storm. It means the distribution of the rainfall in terms of time. Okay, for example, one storm is 1 hour maybe. Okay, so in 1 hour, what is the different intensity of rainfall? Okay, for 5 minutes, what is the rainfall depth? Another 10 minutes, what is the rainfall depth? So that is temporal distribution. And the last one is spatial variability. It means that the location of the rainfall, so it may be different from one point to another point. So that is spatial variability. Okay, next, some introduction on intensity, duration, frequency curve. Okay, so you can see that the y-axis is the rainfall intensity, the x is duration, and there are several frequency. Okay, like 2 year, 5 year, or 10 years. So this frequency is the return period. So how do we expect? Like if it's 5 year return period, so we may expect this amount of rainfall may occur at least once in 5 years, for example. So this is IDF curve, which we use for determining the design rainfall. So this is important for us engineers. Okay, so this IDF curve is developed or is drawn from analysis through different specific rain gauge records at one place. Okay, and because it's related to frequency analysis, which is statistics, so it needs to be, the data should be more than 25 years. Okay, so it will not go more deeper. You just need to understand how do we use this IDF curve. Okay, so this is taken from this MASMA, the Malaysian manual for stormwater. So when you design drainage, you are doing the hydraulic design, you need to get the, if you remember, the peak discharge. Okay, so how do we get the peak discharge? Is we get it from our design rainfall. So usually the design rainfall is taken from this, from IDF curve. So this curve is developed by the Department of Irrigation and Drainage. So it's kind of like a manual. So you can just use this IDF curve. You can either create your own IDF curve, or you can use the IDF curve developed by the Department of Irrigation and Drainage. So let's say you want to design rainfall which has a storm duration of 10 minutes. So you look at the x-axis, and then you want to design it for a let's say a 5-year return period. So you look at this 5-year, no, that's not 5-year, this one, the 5-year line. Okay, 5-year return period line, the second one. So you can identify or estimate the rainfall intensity for this 5-year return period, okay, and the storm duration of 10 minutes. So that is how you use your IDF curve to get the design rainfall intensity. Okay, so this IDF curves is actually derived from this kind of formula. So okay, so this kind of formula which have its constants is different for different station. So this table shows you the station name and the constants. So this constants is actually the one that develop this IDF curve. Remember, this IDF curve looks like this, right? So this constant is the parameter which define these lines. Okay, so different IDF curve is different for different location. For example, this have like in Perak we have 12 stations. So in Perak we will have 12 IDF curve. Okay, in Perlis only one IDF curve. In Selangor we have 10 IDF curves, depending on the location. Okay, so this is example of an IDF curve in Ampang, from which the data are used using Ampang rainfall station. Okay, so we touched on the instruments to record rainfall, and then we already know about the IDF curve. So now what do we do with those data? Okay, the data that we have collected. Okay, so we may do some analysis on it. Okay, so we know the data, we have the rainfall data. So what do we do with it? So we can assess the pattern of the rainfall. For example, the most simplest way is we use a bar chart to see the pattern of the rainfall, to see just to see the pattern of the rainfall depths across months or across a year. Okay, just a simple bar chart analysis. And we have mass curve to see the homogeneity of the data or the rainfall. Later we will look into this, and then from mass curve we can do more assessment using residual mass curve and double mass curve. So I will show you later what are these. Okay, so this is a really simple example of a bar chart. Okay, we have the y-axis, the rainfall depth, and we have the x-axis. It can be anything. It can be month. Okay, January, February, March, April. Okay, and so on. It can be yearly data also, 1970, 1971, 1972, and so on. And it can also be any kind of time period, like hourly, 1 hour, or daily data. So it depends on your purpose. Okay, the other way is we do a mass curve. So what is mass curve? It is actually a cumulative rainfall against time. We have time. It can be any time, daily, hourly, monthly, anything. And then we have rainfall depth, and then a cumulative of each time. Okay, so this is the cumulative from the rainfall depth data. Okay, so if we plot this cumulative rainfall depth against time, so this is what we call mass curve. So what we can see is whether there is some significant changes in the pattern across time. So if the graph has some slope like this, it's not, we can say it's not homogeneous. So it means that across time there is some event, maybe the climatic event, maybe the mostly also external factor, but maybe it can be an error, or it can show some kind of climate pattern. Okay, what else we can do is we can use the residual mass method. Okay, you have the time, you have your rainfall data. Okay, and so what you do is you get the difference between each rainfall data against the average of all the data. Okay, the average of all of this, you get 90 here. You get 90 here. This is the average of all the data. So next, you calculate the difference between each rainfall depth here. You need to minus by the average. So here you get the difference between each rainfall data at each time. Okay, you just minus 90. So then you get this difference. So the next would be is you need to cumulative, need to do some cumulative of this difference. Like here 0, and then 0 plus 10, and then 10 plus minus 30, so you get minus 20, and then minus 20 minus not minus plus, so minus 30, so you get minus 50, and so on. So these are the cumulative of the difference. Okay, so next we plot this cumulative difference as y-axis, and x-axis is the time. So what you can see here is you can see this is if the slope is downwards like this. So this is the dry period. Okay, if the slope is a negative, this is the negative slope. But if it's a positive slope like this, so this is the wet period. Okay, so it's positive wet period. So this shows you the climatic pattern also of your location, where the rain gauge, where the data you get from the rain gauge, the location of the rain gauge. So it may show you the climatic pattern as well. So you know about mass curve, you know residual mass curve. So now you can also do a double mass curve. Okay, so what does double mass curve do is it is used to see whether the rainfall data is temporally homogeneous, means according to time. According to time, is it homogeneous? Homogeneous means it's the same, or there is some break or error. Okay, so that is what we call temporally homogeneous across time. So okay, again, this means that to see whether in time the data has some errors by comparing one station to other station around it. The errors might be due to some external factors. Example, rain gauge has been moved to another location nearby, or there are some changes in the equipment. So this we need to check, because these are part of the process of data error analysis. We want to see if there is some error in the data. Okay, so this is an example of a double mass curve. okay, you need to understand is a comparison between one station, here station X, and a number of neighboring station. Okay, so you compare one station to neighboring station. So both are the cumulative rainfall depth. Okay, both are cumulative rainfall depth. So you plot, I will show you later the example of data. So what you see here, if you plot and you found that there is some difference in the slope. For example here, there are two type of slope here. So this means there is some break point. Okay, so where is the break point? The break point is here. So this is the break where something occur during this time. Okay, so each of this data represents, for example, if we are looking at yearly data, so this represent, let's say 1970 or 19 sorry, so this represent, for example, this is 1970, 1971, 1972. So for each year you have the data, so you know if there is a break here, so there is something happening during this year. For example, if this is 1958, if this is 1958 here, so there are something occur during this year. Okay, so this is an example of the data. Let's say we are testing station X. Okay, we want to see whether there are some external error of the data collection using the rain gauge. So we are testing station X. So we need to have data from the neighboring station. For example, this example shows that we have the average cumulative rainfall for 18 stations. So these 18 stations are the neighboring station. Neighboring means stesen berdekatan, dikelilingi, stesen berdekatan station X. So 18 stations near station X. So we can test whether the station X has some error by comparing the data with stations around the station X. So for example, how do we get these points is, let's say we have data from 1952 until 1970. So we have the data for station X. So this this is in centimeter. Okay, the unit is centimeter. So for year 1952, we have 30 centimeter of rainfall. Okay, this is really small. This is not Malaysia example, maybe some arid country, because it's really quite small. 30 centimeter is similar to like 300 millimeter rainfall. So each year we have this rainfall recorded. Okay, and then we have the neighboring stations around station X. So we average them, average the values of rainfall in all the stations. In this case, 18 station around station X. So we get this average. So that's why we put it average 18 station. Okay, so each year we also have the data. So how do we plot this graph? Is the cumulative. This is the cumulative. Okay, see the word cumulative. So what is cumulative? You can see in this column here. Station X cumulative means that first 30, the next year is 40, right? So the next year we add 30 plus 40 is 70. Okay, and then the next year, 1954, we add some more the data, and then so on until in the end we get this kind. Like in 1970, in the end, the cumulative rainfall data is 518. So we do the same thing with the 18 stations data. Okay, the average 18 stations. So we cumulate it, cumulative. So then we can get this kind of plots. So we get this kind of plots. So what do we do next? We need to find the slope. In this case, we see that there is two slope in the same graph. Okay, if there is no error, we can see that there is only one slope. If there is no error, let's say if there is no error, then we might have a straight line like this. So but here we have two kind of slope. So when is the break? What do you mean by break? Is when is the error started. So if we look at this graph, it seems that the break is in 1958, and there is something happened in 1958. Maybe the rain gauge got moved from to another place, or they change a new rain gauge. Okay, so that is why there is some break here. Okay, so it's okay. So what we do next is we can correct the data. Okay, we can correct the data. So what do we do is we need to let's say we want to correct the future data. You want to correct data in above 1958, 1958, 1970. We want to correct this data. So we need to change the slope. This S2, we need to make it into S1. You understand? We need to make this slope becomes S1, similar to the previous years before 1958. So that is how we correct the rainfall data. Okay, so I hope we understand what is S1 S2. S1 is the slope. Okay, the slope of these two lines, line 1 and slope of line 2. So there is two slope here. Okay. Okay, so we know that we have two slope, S1 and S2. Okay, S1 and S2. So now if we want to adjust the data, okay, because of some error in 1958, so we want to adjust the data after 1958. We want to adjust all of this data. So what do? We have to understand that we want to adjust it to be S1. Okay, and the original or the observed data is from the data of S2. Okay, so we can say that BA adjusted, okay, and BO the observed or original data. Okay, so you need to understand this. If we want to adjust data after 1958, so BA is S1 and BO is S2. Okay, then if okay, this formula is actually comes from PA over BA equals to PO over BO. Okay, so but we want to adjust the rainfall data, right? So P here is the rainfall data. Okay, P is each point, this rainfall data of each point. Okay, so what we do is we get this factor. Okay, PA, P adjusted, we want to adjust or the adjusted rainfall data is equal to we know that BA is S1 and BO is S2. So we just follow this formula. And PO is the observed data or the original data. Okay, so then we just use this formula and we get this relationship. P adjusted, okay, the new P, the new rainfall data, adjusted rainfall data is equals to 1.35 of the original data. So PO, so we know PO, so PO is the original data, okay, for station X, the original data for station X. So this data, all these dots, the data for station X. So we just multiply it by 1.35. So we will have the new or adjusted or PA rainfall data. Okay, so there is another condition if we want to adjust data before 1958. Just now we learned on how to adjust data after 1958, but now we want to adjust the data before 1958. So we remember O is original or observed and A is adjusted. Okay, so now it becomes different. S1 is the original or observed rainfall data because S1 is the data before 1958. Okay, and now S2 is adjusted. Okay, because we want to follow the slope of S2. So that's what we want to follow. We want to the data to have the same slope as S2. So we may say that the adjusted slope is S2. Okay, so you can calculate the slope based on your data. Okay, so we see here PA, the P adjusted. So P adjusted is the data before 1958. We just want to adjust the data before 1958. So follow the formula. PA over BA equals to PO over BO. So we will get PA equals to this formula, and we will get this relationship. So we will get the values based on your calculation. So in the end, P adjusted, okay, P adjusted is the rainfall of station X before 1958. Before. So we will get this factor 0.74 PO. PO is the original or the observed data. PA is the adjusted data, the new data that we want. Okay, so if you realized the slope of S2 is lower than S1, so see the factor becomes less than 1 because it reduced the rainfall data. So it depends on your purpose, which data you want to adjust. Is it before the break or after the break? What do I mean by the break is data is in 1958. 1958 is the break, okay, because the something has changed. The rain gauge were moved or the rain gauge have errors. So we want to adjust the data. So we can adjust it before 1958 or after 1958.